fact, when I postponed it, that was part of my thought. I was like, but you're taking it out, you would be taking out a day, you have nothing else. But also, you know, I was up in Seattle and I emailed Dr. Loris and I said, it sounds like it's pretty bad down there. Do you think we should postpone the switch? She goes, you should. I said, okay. She said, some people might not even have internet. So it really is bad down there. So, everybody okay? Yeah? Okay. Any questions before we get started? Anything, whatever, stuff? Anything? Okay. Test my markers.
Was your house okay?
My house was great.
Okay.
It did better than Matthew. Maybe because all the trees got tested in Matthew. But we're good on markers. All right. Let's begin. So we got 2 lectures to go over today. Moving, especially we'll be fine as long as I don't get too distracted, because you know how I do. Well, you're learning how I do. I like to get distracted. It's fun. So anyway, so diffusion and osmosis is the first one. The next one is mixtures and solutions. There's some intertwining of the topics, and this is where we'll pull in some of the general. You'll see some of that general and organic come into all this, and make a little play there. And I'll try to highlight to you the things that are the most important. It is kind of nice that I'm getting this lecture in before you do your inhaled anesthetics lectures, because some of these things, like when it comes to like your coefficients and that kind of thing, are very apropos, like blood gas coefficients and that kind of thing. So you get a little bit of exposure to that prior to next week. And next week it will be fantastic. I just gotta brag on Dr. Welliver for a minute. I just probably the other reason why I was slightly late is I was rapidly trying to write an email to the 2017 cohort and 2018 cohort, because Dr. Welliver is part of a task force that the Anesthesia Patient Safety Foundation has formed. Anybody familiar with APSF? You will be. The APSF has really risen up in the last 10 years as a very premier organization in anesthesia. So they're always addressing any kind of concern about safety for patients. So they're not, there's a lot of organizations out there that do good things, but nobody's hardly heard of unless that's their thing, but pretty much anybody in anesthesia that pays attention knows what APSF is. Well, anyways, they are doing a task force looking at residual muscle paralysis in recovery. And they're looking at all this stuff, and I have been appointed to be on a expert panel where I'm providing feedback to the task force, basically on my observations of some of the barriers that we'll encounter to making changes in practice and that kind of thing. And so I can kind of bring to the panel anything I want. And so I got to thinking about it. I'm like, who better to say what a lot of the providers out there think, their biases, their opinions, and all like that, than students. And so I sent an email to the 2017s and 2018 saying, what do you observe? When you're concerned about residual muscle paralysis, what's the feedback you're getting from your CRNAs, your anesthesiologists, that kind of thing? Do you see differences from one clinical site to another? Like, is there almost a cultural opinion from one site to another? I imagine there is. So I'm going to take that feedback that they give me, and I'm going to provide that in my discussion piece to the expert panel. So I thought that was kind of cool that we're getting all the way down to the student level here. Yes?
Random, really silly question. So next Friday for principals, we have to wear scrubs. Do you want us to bring our student business casual attire since Oliver's going to be here?
What do you need to wear scrubs for?
No, but
No,
also
for
Oh,
Friday
oh,
with
okay.
hypothermia. Yeah, we have to wear
She wants us in
scrubs.
scrubs.
Oh.
So do you want us
On
to
Friday?
train?
What are y'all doing on Friday in her class?
She wants to see us in scrubs to make sure we're presentable.
Well, and we have malignant hyperthermia
After the exam.
And we'll be listening to each other's stuff.
Oh.
and lab coats. So do you want us to pack clothes?
No, I think that's fine. I think if you're all in scrubs, that'll be a little bit more appropriate than some in scrubs and some not.
Sorry, I know that's silly. Just
No,
wanted to-
I actually appreciate the question. You know, we always like to put a good foot forward when we have our guest lecturers, but, so thank you for bringing that. So if that's what she said, I think that's fine, and, you know, maybe it'll become apparent to him why, but that's good. But anyway, so bottom line is, that has nothing to do with today's lecture, except that it's a big deal. I mean, there's this task force he's on, they've chosen 10 people in the country to be on this task force, and he's one of them. He actually just at A&A led an entire workshop the day before the conference started on this topic. So like people registered, paid $300-something for this workshop and all, and he was the leader of the workshop. He's a guru when it comes to muscle relaxants, but he knows his inhaled anesthetics as well. So anyways, see how I do? Anyway, all right. So diffusion. Diffusion is the process of movement of one type of molecule through space as a result of random motion. Randomness is entropy. So just when I even move my hands through the air, I'm then causing a random spread of the molecules of air that I'm moving around. And so that diffusion occurs all the time. So if diffusion is even occurring in this area, it doesn't have to necessarily pass a membrane or go from one medium to another. Diffusion is just a process of moving from one place to another. So you can have diffusion that's occurring where you have a freely diffusible plane where whatever molecule, in this case N2, it should really be N2, can move from one side to another of this plane. And you can also have diffusion where only one thing can pass through. And that's where you start getting like gradients and that kind of thing. So we'll get into that a little bit more. So you have let's say you have two divisions of a container separated by a permeable membrane. Permeable meaning things can pass through. And we'll even talk about the membrane thickness being delta X. Delta in science means one of two things typically. What are they? Change or heat. And the only time it usually means heat is like when you see in a chemical reaction. But you know, whenever you see delta X, that means change in thickness. Okay. So if you have one area with this permeable membrane that has a greater concentration, let's say, of oxygen, like your alveoli, for example, looking back at the previous slide, is what we're trying to describe. One area that's got a higher concentration than another, as long as that membrane allows that molecule to pass through, you will have diffusion. And so you have that higher alveolar side that will then drive the net movement of that molecule into the other side. So diffusion basically explains why when we increase the concentration of oxygen in our alveoli, you'll increase the concentration of oxygen in your plasma. And so, but the process of getting that oxygen from our alveoli to our capillaries, to our cells, it's all diffusion. What is the difference between diffusion and osmosis?
Semi-permeable membrane. Oh, it's movement of water.
What's movement of water? Osmosis. Diffusion is movement of the solute, the thing dissolved in the water, or any molecule. Okay, so make sure you get that distinction. When we talk about osmosis, the solute, the thing dissolved in water, is not moving. It's the water that's moving. So right now we're talking about diffusion. Bless you, bless you, bless you. So we have the partial pressure of oxygen in the alveoli here, trying to make its way into the capillaries here. And this process of moving from here to here is diffusion. We'll talk about different factors that affect the ability for that diffusion to occur, one of them being membrane thickness or problems with the permeability of that membrane. So when you have a semi-permeable membrane, meaning permeable to some things but not another, so when we just use the word permeable, there's no like selectivity. When we say semi-permeable, now we're saying something can pass through but something else can't. So like take plasma proteins, for example. If our capillaries have good integrity and we're not septic or we have some major problem with the capillaries, plasma proteins stay in the plasma. They don't leak out. Water, however, can pass through and move through capillaries and all like that. So what we end up having when we have this semi-permeable membrane is we then have some pressure gradients that stay stable. And that can cause some kind of movement of water as opposed to just the diffusion. So, for example, what I'm getting at is if the plasma proteins can move into this section just as easily as being here, what we more see is the plasma proteins creating an equilibrium. But because the plasma proteins cannot pass through, water will move instead. So water is freely permeable and attempts to distribute equally in whatever. But because that protein or sodium ions, for example, cannot easily pass, water moves instead. That process is osmosis. So osmotic pressure is related to the number of non-permeable molecules, or that solute, that cannot pass. And that's a key point, because if the solute can pass, diffusion, right? But the solute that cannot pass creates this osmotic pressure. Even if the solute can pass, you'll get that osmotic pressure, but the only way you'll get some kind of gradient in that is when there's solutes that will not pass, thus pulling water in one direction or another. The second bullet is a little confusing. Osmotic pressure is the pressure to stop osmosis. I think that's a little bit like, makes it a harder way to think of it. Bottom line is, when you think of osmotic pressure, think of it as pulling power for water. The higher the osmotic pressure, the more it's going to pull water. That's the like Physics for Dummies book definition. You know? But it's practical when you think about, and we're going to get into this, like solutions that we use for fluids, crystalloids. The ones that will keep water in the plasma more have a higher osmotic pressure, have more osmoles. Oncotic pressure is related to proteins. So when we talk about osmotic pressure, we mostly are thinking about solutes, ions, sodium, chloride, potassium, things that are charged that don't pass very easily through lipid membranes. And yes, water is polar, but it can pass through lipid membranes. Thank goodness, or else whatever water's in our cells is what it is, and you can't ever move it in or out. You know, so but it's certainly not as readily movable as something that is non-polar, but it's more movable than an ion. So, all right. And so normal oncotic pressure is about 24 to 27 millimeters of mercury. Osmole. Osmole is a gram molecular weight of an undissociated solute. What? Okay, let's make it a little more easy. An osmole is how many moles of a solute that is in a specific amount of solvent. So one of the things that I eliminated from the first 2 lectures I give, and it comes up in the next lecture, so it's still there, but it used to be taught earlier, and it gets a little convoluted when I do these 2 lectures because I try to decide which one to teach first. You know, do I do this one first or do the next one first? Is the concept of molarity. And this is where I might need to rearrange the whole thing to make it a little better, because it helps you to understand this when you understand the concept of molarity. Molarity is a much more simple concept, so we're going to go ahead and jump ahead a minute to the next lecture. I'm not going to pull it up, but a mole, 1 molar substance is a mole per liter of solution. We know what a mole is, right? Besides a furry little annoying rodent, right? So 1 mole is Avogadro's number. So if we're talking about 1 mole of sodium chloride, we're talking about 6.022 times 10 to the 23rd sodium chlorides. 1 molar, you have to forgive me, I've been up all night doing epidurals and stuff. 1 molar sodium chloride is a 1 mole of sodium chloride in 1 liter of solution, most likely water. Remember, anybody remember all this? Molarity, molality? Yeah, vaguely. So if we say we have a 1 molar solution of sodium chloride, then basically we have, what is it, like, I think chloride is 35 something grams per mole, and sodium is, one of them is 35, one of them is 45. It's about like 80 or so. You'd have about 80 grams of sodium chloride, or 80 grams of table salt in a liter of water. That would be a 1 molar solution. Where in chemistry, where you mostly saw molarity, if you remember back, it's mostly like acid concentrations. You know, this is 1 molar sulfuric acid, and that's what I could really cause some smoke with this stuff. You know, I was the really bad student in college. I'm at UF, go Gators, and I'm taking this. I mean, I don't know. This is one of my favorite classes of all time. Did anybody take Chem 2? Like not the 1000 level, but the 2000 level, where you had lab and you were given like this solution, and you had to figure out all the solutes that were in it. You did all these tests to it. Oh, did you like it? It was so cool. I mean, but then at the end of the day, you're supposed to like dispose of it in the proper way. I just throw it all in the sink and I put water on it and start smoking. Oh, I didn't need to do that. But I tried to be pretty. So anyways, and look, I got these numbers right here, 35 and 23. I was way off. I thought 35 and 45. Anyways, so that's molar. But when we talk about solutes in solution, and we want to talk about even ions, it really helps to start talking about in terms of osmoles. So the osmoles are these dissolved compounds that are in water, and each part of this, like sodium chloride, counts for an osmole, because what happens when you dissolve that sodium chloride, it becomes sodium ions and chloride ions. So now you have 6.022 times 10 to the 23rd sodiums and 6.022 times 10 to the 23rd chlorides, and we want to count those two for our osmoles. So if you have a mole of sodium chloride, yes, you're 1 molar sodium chloride, but you're 2 osmolar solution, because one is from the sodium and the other is from the chloride. The reason why I have the potassium chloride on here is because the osmoles don't have anything to do with the weight or the mass of that solute. For example, a mole of potassium chloride, it weighs much more than a mole of sodium chloride. However, if you have a mole of potassium chloride, you have 2 osmoles. Okay? You still have 6.022 times 10 to the 23rd of each item, the cation and the anion. So, see if you're following me. You have 58.5 grams of sodium chloride in a liter, and then you have 58.5 grams of potassium chloride in a liter. Which one has more osmoles? It's not the same. Let me say it again. You have 58.5 grams of sodium chloride in a liter,
Okay.
and then you have 58.5 grams of potassium chloride in a liter.
This is sodium.
Which one has more osmoles? No.
No, it's the sodium because those are each one, and then the potassium is less than an osmole of Kc.
Sodium chloride.
All right. Yeah.
So if 1 mole of sodium chloride is equal to 58.5 grams,
It's constituent.
and 1 mole of potassium chloride is equal to 74.5 grams. All right. And now I'm telling you, you got 1 liter that's got 58.5 grams of sodium chloride, and another liter which has 58.5 grams of potassium chloride.
More sodium chloride.
Yeah.
How many moles of sodium chloride are in this one?
1.
1 mole, right? How many moles of potassium chloride are in this one?
Less than 1.
Less than 1.
Right.
So this will have more osmoles.
Right.
So when it comes to osmoles, the mass or the size of the molecules is irrelevant. Okay? Avogadro's hypothesis has to do with gas, and it's a different thing.
But it's the concept that it's how many atoms you have, not the type of
Right.
atoms.
Avogadro's number is always about the number of the thing, not the size of it or whatever. Okay? I mean, even though it doesn't really apply, Avogadro's hypothesis could be elephants or it could be ants. Doesn't matter. It's the number. Okay? Now, why this becomes so interesting and relevant is, have you ever wondered why 3 grams of calcium gluconate is equal to 1 gram of calcium chloride when it comes to the ionized calcium effect?
Yeah.
You're like, maybe calcium chloride is more powerful. It's got like turbocharge or something. Or maybe the mass of gluconate is much larger than the mass of chloride. So when you're measuring in terms of grams, right? You're saying 1 gram of calcium chloride, 1 gram of calcium gluconate. Well, the 1 gram of calcium gluconate, a lot of that gram is the gluconate. So you're going to have less Ca++s in that 1 gram of gluconate, calcium gluconate, than you will in a gram of calcium chloride. It's all about the number of calcium Ca++s you get. And you get more with a gram of calcium chloride than you do with a gram of calcium gluconate. So, osmolality is the same thing basically pretty much as osmolarity. Whenever you see lality, you're just changing the denominator. Instead of a liter solution, it's a kilogram of water. So, what is the mass of 1 liter of pure H2O liquid? If I have a liter of water, liquid water, what is its mass? 1 kilogram is exactly the answer. Very good. 1 kilogram. What is the mass of 1 milliliter of water? 1 gram. What is the volume in milliliters of 1 cc?
1 liter.
What is the volume in milliliters of 1 cc?
One.
1. Right? We've gotten away from even saying cc's, although we say it all the time, but we don't write it, right? You know, we say it, but we don't write it because, you know, Jacob will get us. But really, we all know that 1 cc, 1 cubic centimeter of water, is 1 milliliter of water. It's also 1 gram of water. Makes it nice and easy. 1, 1, 1. So if you have a kilogram of water, that's 1,000 milliliters of water, which is a liter. Okay? So, in the terms of osmolarity to osmolality, same thing with molarity and molality, when water is the solvent, they're basically the same. Because one, the denominator is a liter solution, the other, the denominator is a kilogram of solvent, water. They're the same. So, they're not quite the same because one doesn't take into account the dissolved solutes, but they're virtually the same. So, you can almost, for our purposes, intermix them. I just want you to know the difference by definition, okay? Here's where it gets fun. What's the normal serum osmolality? It's right there, right? What's normal serum osmolality? 285 to 295 milliosmoles per kilogram of water, because we're talking about osmolality. So what's the normal osmolarity in the plasma? 285 to 295 milliosmoles per liter, pretty much. But we use osmolality when it comes to serum, and so that makes it nice and simple because we're only talking about the plasma. And so this is the normal serum osmolality. So when you were in nursing school, RN nursing school, you learned about hypertonic, isotonic, and hypotonic solutions. And we put them in one of 3 boxes, and that was kind of the end of it. That's RN level. You're no longer at RN level. Okay, so now you need to think of the crystalloid solutions you choose in terms of what is more hypertonic than normal serum and what is less tonic or hypotonic to serum. So anything that is greater in osmolality than this is hypertonic relative to normal. I'm not saying you call saline hypertonic, but relative to, like normal saline, relative to that, it is. But when you're trying to choose your crystalloids and you have certain goals for your patient, that's the kind of things you need to be thinking about. Am I going to choose this solution? If when I choose this, is it going to cause diffusion of water out of the vessel, and therefore interstitial, intracellular, or is it going to cause did I say diffusion? Osmosis of water into the vessel. We'll get to that in a minute. How is serum osmolality calculated? You should know that formula. But so okay, it's coming. All right. I get a little off the chart. I'll get back to that in a minute. All right. Osmolarity, concentrated solute in terms of osmoles per liter of water, pretty much the same thing. A mole of any solute in 22.4 liters of solution at 0 degrees Celsius will exert an osmotic pressure of 1 atmosphere. 1 atmosphere is normal atmospheric pressure. Okay? Like perfect, like 1,030 millibars. Anybody know how low some of these hurricanes have gotten? Anybody pay attention to that?
Yeah.
What? I think I saw a 909 on Maria one time. That is so dang low. I think you'd feel it, like you'd feel like, oh my gosh, I'm gonna like explode. I'm almost in space vacuum here. Not quite, but really, I mean seriously, that is really low pressure. I mean, some bad hurricanes have never, some really bad hurricanes have never gotten below like 920, 930. Yeah, 909. I'm pretty sure I saw that. I was like, what? It's in the like, not even in the teens? Holy cow. But anyways, so 1 atmosphere is normal atmospheric pressure, non-hurricane compatible. So anyways, so bottom line is if you have 22.4 liters of solution at 0 degrees Celsius, the osmotic pressure is 1 atmosphere if you have a mole. In a mixed solution, the osmotic pressure is the sum of all the individual molarities. And over 99% of plasma osmolarity is due to electrolytes. So, and like I said, osmolarity, osmolality generally in our dilute solutions are about the same. So when we learned about hypotonic, hypertonic, and isotonic, it was always about whether or not the red blood cells will pop or shrink, right? And it was like, if you give half normal saline, your blood vessel, all your RBCs will do what? Half normal saline. What did we learn? They'll swell and pop, right? They'll full burst. Not really, right? But that's the way you learned it. Well, now you see that RBCs won't even lyse until your osmolarities get below 200. So what we're saying is, if you surround that RBC with a osmolarity of less than 200, where's that water going to go? It's going to go into the cell, so much so that it finally will lyse. 200 is awfully, awfully, awfully low. Okay. If someone has a serum osmolarity of 200, that's really, really low. All right, but capillaries are impermeable to plasma proteins, and so that causes that oncotic pressure that we talked about earlier. This is where I think it's a really good thing to learn. And if you remember this, because 80% of you won't a year from now, just saying, just from experience, you won't. But if you remember this, even if you don't remember the exact numbers, but if you remember close, then you're ahead of just about everybody out there, because there are some real practical uses of these numbers that your colleagues will, that don't know the numbers, they'll know in practicality, but they don't know why. Example, you're going to do a neuro case for a brain tumor, and your patient needs to not have a swollen brain, right? We don't use LR in those cases. We don't. Everybody knows that. Nobody knows why. No. Yes, they do. Some people know why, but not to this level. Bottom line is, normal saline is the crystalloid of choice for those kind of cases, or any kind of elevated intracranial pressure case. You're going to use normal saline, not LR. We use LR for almost everything else. If you haven't been in the OR much, you'll see that very quickly. Saline is not our #1 crystalloid. LR is definitely our #1 crystalloid. But if you give someone LR and you want to prevent cerebral edema, all you're doing with giving an LR is you're giving them a crystalloid that has a lower osmolality than normal serum. So the fluids that are in the serum will want to do what? Because you just gave it dilute solution. Leave. We don't want that. We absolutely don't want that. If anything, we want to pull in. We want to keep pulling in. So we want to give something that's slightly hypertonic relative to normal serum. So as much as you learn that both of these are isotonic solutions, one of them is actually hyper to normal, the other one's hypo to normal. Now, LR's got some major benefits over saline for other reasons, but when it comes to that, not so much. And that's the principle. How many people have used like super hypertonic saline? Like 23.4%. Is that what it is? 23.4%. How many mLs usually? 50 to 100, something like that. How much?
Smaller volume.
How much are you using usually? Not even 100, like 50 mLs? Yeah. I've used it like only twice, because I never used it as an ICU nurse, and we usually don't get that crazy in the OR, but once or twice we got that crazy. But the whole purpose of that is to put all that solute into the plasma and just have massive pulling power of fluid, osmosis, into the vasculature and get it out of the interstitium. Okay? So for requirements for osmosis, across cell membranes, the membrane must have we must have a membrane that is impermeable to one or more solutes. So and then you must have a difference in the concentration of those solutes. Because it doesn't, let's say it's saline. Let's say it's sodium. It's not permeable to sodium. Well, if the concentration of sodium in the cell and out of the cell is the same, you still won't have any osmosis. So there has to be a concentration gradient between the two, and it has to be impermeable to that solute, otherwise you'll just have diffusion. Across capillary walls, most capillary walls are permeable to small solutes, sodium, chloride, etc., but not albumin. Okay, good old Fick. So there's a joke out there about me that if I'm going to, we call it pimping. That's like the inappropriate, or not inappropriate, but it's just not the technical thing for the Socratic method of education in the operating room, where when you're sitting there and I catch you at the most inopportune moment and I ask you some questions, you know, just to see if you're still catching up with your studies, because you all must study this stuff regularly. Don't fall in that trap of being here a year from now and have not reviewed material and be that one that's like, I forgot everything I learned except the stuff I do every day. Don't be that person. There's always one or more. But anyways, but the big running joke on me is if I ask you a question like whose law says blank, it's either going to be Fick or Henry. And so the more that's the running joke about me, I try to ask questions that don't have anything to do with either one of them. Just on Wednesday, a student was presenting on an aneurysm, and I asked about whose law says that wall tension is directly proportional to radius, and I could hear, the joke was there were a couple of people in the class, but they knew it wasn't Fick. It's actually law of Laplace. But of course, the big joke is I would just ask about Fick, because you know what, Fick is a big deal. Fick explains so much that happens in our body. Fick is the father of laws of diffusion. So when it comes to diffusion, your first answer is Fick. Now, I will get into specific laws that are more specific. They have to do with diffusion, but they're very specific circumstances. But when it comes to when it comes to diffusion, it's Fick. This equation I have for you here, you do not need to memorize the equation. Okay, I won't ask you this equation. Fick's equation actually can be applied to many different circumstances, and when that happens, the equation changes. For example, this equation is specifically for fluid membranes and specifically for oxygen. So if you look up Fick's equation on Wiki, which is not the best place to look for it, you won't see this equation at all. This one's applied to the movement of oxygen from alveoli to capillary. But what you really need to do is get the principles of what is necessary for diffusion. And you will always have the same elements in any Fick equation. Diffusion is solubility / diffusibility, any of those things, the ability for something to be dissolved or move, times concentration gradient divided by some ability to, like some barrier to getting that across. In the case of capillaries, membrane thickness. So if somebody has, let's say, ARDS, although it's not necessarily an issue of thickness, it's an issue of just that permeability and all like that, there will be an impairment to diffusion. Okay? So Fick's law is not so simple as one straight equation. We'll get to Fick. We'll get back to Fick in a minute. Pulmonary gas diffusion. This will come up again, but I'm going to go ahead and write this equation. I think I did this already first day. This equation you must learn. I won't ask it on the chemistry quiz. And nothing will change about that quiz. Like, just because we're covering stuff since then, it's not going to be on that quiz. The stuff that was going to be on that quiz is still the only stuff. Even though Dr. Welliver will be speaking on halogenated ethers next week and naming all that stuff, just because he's had it before your quiz, that's not for the quiz, okay? Nothing has changed about that. But, exam 1, it's on, all right? So, this equation, you must know. Now, it doesn't matter if this is here or that is there. Either way works. So water plus carbon dioxide forms an equilibrium with carbonic acid, which is the center part, which also forms an equilibrium with bicarbonate ion and H+, which is pure acid. You might see the equation written somewhere where this H+ is instead H3O+, which is the hydronium ion. I'll talk about that a little bit more when we do our acid-base lecture, and that's where it's really on. When we get to that acid-base lecture, I can't remember if that's going to be on exam 1 or 2. Depends on what comes first, acid-base or exam 1. I think acid-base comes after exam 1. Is that right? Anybody know? Look on the calendar. Anyways, when we do the acid-base, this equation is big time on. Okay, but this equation is very important. Yeah, so if you see the H3O+, that's fine too. But what we have here, this is happening in our bodies constantly. It's also happening in your Diet Pepsi right there, constantly. You have this equilibrium between carbonic acid and a bicarb hydrogen and water and carbon dioxide. It's occurring all in our plasma, in our RBCs. Oh my goodness, there we are. And you can see that equation right here. Right here. See it? Except in this case, it's not showing equilibrium. It's because there's this constant process. There's a carbonic anhydrase is involved and like that. I'm not going to get into that too much today. But what we do see is we have this equation going on in our plasma all the time, and it is in equilibrium. It doesn't go only one direction. But the process of removing acid from our plasma is this process, getting CO2 out. That's later. How do we get rid of acid in our bodies?
Breathe it off.
What?
Breathe it off.
We breathe it off, or we pee it out. That's right. That's for another lecture. Those are the two ways, though. The two primary ways of getting rid of acid in our body. All right. Back to Fick's law. So Fick's law of gas diffusion across the fluid membrane is directly proportional to the partial pressure gradient, membrane area, which wasn't really depicted on the previous equation, but it's a very important piece, and then the solubility of gas in the membrane. Let me go to a very important aside here. Let's do a little algebra. Oh, I know you hate it, right? And then a couple of years like, what's he going to do with this? What's he going to do? All right. We use the terms directly proportional and indirectly proportional a lot in this course. And I think it's important. Let me add something here. It's important for you to, when you look at an equation, to be able to see what elements would be directly proportional to what and what would be indirectly proportional. Let's back up a minute. What do I mean by directly proportional? That means that if one item increases, the item that's directly proportional to it will also increase. As opposed to an indirectly proportional, whereas if one item increases, the other item will decrease. All right? So when you look at an equation, there are certain principles of algebra that tell us, just by looking at it, those things. For example, let's look at A times X. This is an equation. That means it has to all come back to the same, right? So if we don't change anything here, we don't change C, we don't change D, we don't change B, but we increase A, What has to happen to x for the equation to stay equal? For all things to stay the same? It has to decrease. That means that if you look at two elements on the same, whether it be the top of in the numerator or the denominator, times each other, they're indirectly proportional. Okay? Now, if B increases and A, X, and C stay the same, what has to happen to D? It has to increase. Because if it doesn't, the equation's shot. I could throw some numbers in there, but we don't have time. You can play it. You can substitute 1 for A and 2 for whatever. You can mess around and figure it out. If I were to eliminate the X for a minute, let's just leave it off. If it helps you to do it on the numerator. If A increases, C has to increase. Or how about this? A equals B. If A increases, does B not have to increase? If A was 1 and B was 1, and now I turned A into 2, B is now 2, right? So whenever you see two things on the same, like two things in the numerator on opposite sides of the equal sign, they are directly proportional. Whenever something is on the same side, but like on the same side of the equal sign, but one's in the numerator and one's in the denominator, these are indirectly proportional to each other. Okay? So all those things help you, when you see an equation, if I give you an equation, you don't even have to memorize this slide. All you have to do is look at the equation and use algebraic principles to answer the question. That being said, you do need to know these things. So, what I'm saying is, the more you have a partial pressure gradient, the more membrane area you have, the more soluble that gas is in that membrane, meaning it can pass through, the more diffusion you're going to have. Directly proportional. It's inversely proportional to membrane thickness and the square root of the molecular weight. And this is the one piece that is not truly Fick. Fick doesn't get any credit for this piece right here. Anybody know who gets credit? Nice one. Not Henry. Henry doesn't get this one. Graham. It's coming up. So going back to this, when you think about breathing in air and then giving a patient a nasal cannula, and you turn that cannula on, and let's assume they breathe, and all of a sudden more oxygen goes into the alveoli. What do you think what was the FiO2 prior to turning the nasal cannula on? 21%. What do you think the end tidal oxygen was? Like, what were they breathing out? What do you think?
Oh gosh, what's the proportion of?
Anybody know usually what that is? No, not CO2. Oxygen.
Yeah. Yeah.
Yeah, it's usually about 17. There's a gradient there. You know, a lot of times you'll see 17. It depends on how they're ventilating and all like that. You know, if it's half, if it's 10, they're not ventilating a lot. They're holding on to that. You know, they're holding on to that, really holding it on. But it does depend on how much they're ventilating. But the bottom line is it is less, right? But let's say it's 21%, and the capillaries have, let's say, 21% normally. All of a sudden you go to, let's say, 35% FiO2. Now you have increased the concentration gradient. The difference between the alveolar oxygen and the capillary oxygen just got much larger. What happens to diffusion? Goes way up. What if someone is breathing 100% oxygen, and they've been breathing 100% oxygen for an hour, and they've been breathing well, they got great lungs. I don't know why we were doing that, but we were doing that. They're breathing 100% oxygen, and all of a sudden, we take the oxygen away and they're breathing room air. What happens to diffusion? It goes what?
The oxygen will cross back.
So it increases or decreases? Increases.
It goes the other way.
Diffusion doesn't have to be just one direction, right? So you would establish an equilibrium between the alveoli and the capillaries, and all of a sudden you significantly decreasing the alveoli, suddenly you have a lot of diffusion going out. Right. Think both ways, right? Right. All right. Okay. Fick's law explains, and this is where I'm going to kind of rush over a little bit because this is really uptake and distribution, that kind of thing. But it explains concentration effect, second gas effect, diffusion and hypoxia. These are great concepts to look at. By the way, who has already jumped ahead and watched the Eager DVDs? Thank you so much for doing all that. How much does, I can't remember how much he talks about things like diffusion and hypoxia. Does he talk about it?
Not a whole
I'm
lot.
surprised if he doesn't.
Kind of glazes over.
Yeah,
Yeah, he does mention it.
he does mention it, but that's about it. Doesn't talk about second gas effects much. It's because he's too busy talking about death. Can you not tell he was paid by Baxter to do that whole thing?
Yeah.
Oh, he was big time in Baxter's pocket. Oh yeah, oh yeah. I mean, what about the video of the induction, right?
Yeah.
I mean, that patient was so snowed with narcotics. You know, I mean, that patient's like, yeah, I'll breathe. I don't know, like cyanide gas right now, or whatever, you know. Anyway, but yeah. Anyways, yeah, desperate induction is kind of silly. By the way, he came to Chan's UF Health once and gave a lecture, and went to the OR and did a couple of desperate inductions years ago. I was there. I thought that was kind of cool. I was like, that's eager. I just finished school.
Yeah.
That's it.
Yeah.
But he's probably really, really old now. But anyway, all right.
He did.
Did he?
Yeah.
Aww. When? Really? How'd y'all know this and I didn't?
Well, and it was in the CRNA ward too.
Wow.
And you were in Seattle with the CRNA.
Yeah, 2 weeks ago.
Yeah, it was. Yes.
Yeah, that's another sign. I didn't do any Facebook except the last day I was up there because I just seen in very bad taste and say, we're having a wonderful time! when everybody else is drowning, you know, so it just didn't seem right. So, I was like, I asked my wife, I'm like, no Facebook. Seriously. It's just not cool. She's like, you're right, that's not cool. So, but we are having a great time. I'm like, I know. It's our secret. You know? So, anyways, all right. Factors determine diffusion rate across membranes for non-gases. So, because it's not just about gas, it's not just about oxygen and carbon dioxide like that. It's about a drug you just administered, IV, right? So, concentration gradient for unionized substances, because when it comes to like that drug, if it's ionized, it's not going out of the plasma anyways, right? Water-soluble drugs stay in the plasma. Muscle relaxants is an example. Most of the drugs we give, we like them to be very unionized. That's how they work. But for non-ionized substances, that stay there, so there's no diffusion. Electrochemical gradient for ions. Interesting. So there's not just the whole concentration gradient thing. There's an electrochemical gradient. So if you have a cell membrane, and inside the cell, there is very little sodium. Outside the cell, there's lots of sodium. Okay? So here's the membrane. A little bit of sodium, lots of sodium. Is sodium going to pass the cell membrane to get in?
It's a small molecule.
It's charged. No.
Oh, it's not.
Right? It's not going to pass. Right? How does it get in?
Sodium potassium ion.
No.
Ion channel?
Not the pump.
Really?
Ion channel?
Pumps always go against concentration gradients. Sodium potassium pumps, why sodium's out there. Okay? Channels. Channels will open, allowing the sodium in. Okay? When that channel opens, there's this big concentration gradient, lots of diffusion, rushes in. There's more than that though, because sodium is positively charged. And what's the general charge inside a cell? Always negative.
Yeah, it should be.
Always negative. Whether it's negative 70 millivolts, negative 90 millivolts, or maybe at a depolarized state of negative like 40 to 50, which is still negative. It's still polarized. We call it depolarized, but it's really not. So now you don't not only have all these sodiums want to go in, but you also have all these positively charged going, oh, it's negative in there. And so it's like, wait, I mean, it's fast. And so that's another thing that can affect diffusion. And then lipid solubility and size. The bigger the molecule, the slower the diffusion. All right, so going along with what I was saying about the charges, the Nernst equation, which I don't make you calculate, I don't even know how to. I did it once. It was a long time ago. I forgot. I don't care. But the Nernst equation is how you get that negative 90 millivolts or whatever. But that process, when you're looking at that depolarization,
Those are fast.
you're seeing sodium flowing into the cell, but it's not just because there's a bunch of sodium here and a little bit here, but because there's a bunch of positives here and a bunch of negatives here. Okay? What makes that all possible? The sodium-potassium pump. The sodium-potassium pump is pumping out a bunch of, it's moving positives around, but at an uneven number because of the size of the molecule and all, and so you end up getting more positives outside the cell than in. Graham's law says the diffusion rate of a gas or liquid is inversely proportional to the square root of its molecular weight. So it is an impairment to diffusion. And we kind of throw it into the Fick's law thing, but Fick doesn't get credit for it. But bottom line is big molecules diffuse slower than small molecules. All right, there you go. So diffusion through a tissue sheet, Graham's law, Henry's law, and Fick's law all apply to tissue diffusion. And fast facts, nitrous oxide, N2O, the 2 should be small. I need to keep wanting to fix that. All these 2s, I didn't originally do these slides, obviously, and I don't know. I always like to do the subscripts, but anyways, just 1 second. Nitrous oxide is 36 times more diffusible than nitrogen. Thus, you wouldn't want to use an air, like when there's an air-filled cavity. It's just highly diffusible. CO2 and nitrous are approximately 20 times more diffusible than oxygen. It has atelectasis implications, and the main determinant of gas diffusion, when all other factors are equal, is the concentration gradient. In other words, if there is no concentration gradient, it doesn't matter about, none of the other factors matter. It could be super soluble, lots of membrane area, very little membrane thickness. If there's no concentration gradient, there is no diffusion. Okay? Yes, sir?
Is the Fick principle the same we use to calculate cardiac output?
That's correct. Maybe a
The
derivative.
Fick method?
Well, cardiac output is what? Stroke volume times heart rate. I must admit, I'm even drawing a blank, but is that
there's a Fick,
the Fick method is
There's
called?
a Fick method. It's like has to do with.
You draw an AVBG and a
hemoglobin.
BBG, and you use the oxygen usage, and it's over another factor.
Oh, and so therefore come up with a cardiac output. Like that's how the machines do it.
It's
Yeah,
a
yeah.
derivative.
Yeah, I gotcha.
Yeah.
I don't know.
Oh.
Yeah. So. All right. What time is it? 11:20. Oh, I was thinking I was doing worse than that. All right. So what time is your next class? 1 o'clock?
1.
And y'all need to get lunch. So the goal is to be done here no later than 12:15. Y'all got 5 minutes. 5 minutes. And we're back on it.